Prove each statement in 8 through 23 by mathematical induction. 7 to the n minus 1 is divisible by 6 for each integer n greater than or equal to 0. So the first thing I'm going to do is I'm going to identify what my propositional statement P of n is. So we're going to start with the base case, which is the smallest positive integer that satisfies the statement P of n. And that would be n equals 0, since n is greater than or equal to 0. So what is P of 0? P of 0 is what we get when we plug in 0 into this sentence here, which would be 7 to the 0 minus 1 is divisible by 6. Now, what I'm going to do is I'm going to put a little question mark here because I don't want to just replace my n's with 0. Otherwise, I would be assuming the thing that we need to show. We need to show that 7 to the 0 minus 1 is divisible by 6. So if I put a question mark here, this allows us to avoid circular reasoning, where we start with the conclusion that we're trying to show. So what I'm going to do is I'm going to evaluate what 7 to the 0 minus 1 is, which is 1 minus 1, and that's 0. And 0 is the same thing as 6 times 0. So I put a little check mark here to show that we've verified that 7 to the 0 minus 1 is divisible by 6. So now let's move on to the inductive step. Okay, so the beginning of every inductive step is going to be the same for mathematical induction. We're going to say let k be an arbitrary integer with k greater than or equal to 0. We use 0 in this case because that's our base case. And we assume that P of k is true. Now, P of k is what we get when we take P of n and we replace all of our n's with k's. So this is 7 to the k minus 1 is divisible by 6. So we get to assume that this is true. Now we can be a little bit more clear about what this means. If 7 to the k minus 1 is divisible by 6, then this means that 7 to the k minus 1 is equal to 6x for some integer x. Now the next thing I want to do is I want to lay out what it is we want to show. Now we want to show, and I actually write WWTS to mean we want to show, we want to show that P of k plus 1 is true, which would be that 7 to the k plus 1 minus 1 is divisible by 6. So we have to prove that this is true, and we get to use this fact right here as a tool to prove that P of k plus 1 is true. So what is it that we're trying to show? We're trying to show that 7 to the k plus 1 minus 1 is divisible by 6. How do we do that? Well, we can take 7 to the k plus 1 minus 1, and we can try to algebraically rearrange this in such a way so that we can factor out a 6. Now, that's going to be pretty tough because if you notice here, there's no real clear way as to how we can factor out a 6 to show that this is divisible by 6. But that's where the inductive step is going to come in handy. Now, if you want to use the inductive step, we have to recognize what the inductive step says. The inductive step says that if we have a 7 to the k minus 1, we can replace that by 6 times x. But we don't have 7 to the k minus 1. We have 7 to the k plus 1 minus 1. And so if we want to get a 7 to the k minus 1, we have to change this exponent to just a k. The way we can do that is we can write this as 7 times 7 to the k minus 1. Now we're a little bit closer to the inductive hypothesis. However, we have this 7 here, and the 7 is not a part of the inductive hypothesis. And so we're going to split this up into a 6 times 7 to the k plus 1 times 7 to the k, and then minus 1. Since if I have 6 7 to the k's and I add another 7 to the k, then I have a total of 7 7 to the k's. But the reason why I write it like this is so that we can get a 7 to the k minus 1. And so now we'll be able to apply the inductive hypothesis to this new expression because we've simplified it in such a way that we have a 7 to the k minus 1. Now, if you notice, it might look like we've made the expression more complicated. However, the goal of mathematical induction is to prioritize the inductive step, which means we have to find a 7 to the k minus 1 somehow. And if we can do that, then we can use the inductive hypothesis. And once we use the inductive hypothesis, we'll usually be just a few steps away from finishing the inductive step. Okay, so let's use the inductive hypothesis now. Now, instead of writing 1 times 7 to the k, I'm just going to write 7 to the k. And then I'm going to replace this 7 to the k minus 1 with 6x. So this is equal to 6 times 7 to the k plus 6x. Since 7 to the k minus 1 is 6x, by the inductive hypothesis. Whenever we use the inductive hypothesis, we need to clarify that we use the inductive hypothesis. And now, if you notice, we can magically factor out a 6. It's like a 6 came out of nowhere, and now we have 6 times 7 to the k plus x. Now, 7 to the k plus x is an integer, and we'll call that integer y. So this is 6 times y. And what is 6 times y? Well, that's my 7 to the k plus 1 minus 1 is 6 times some integer y. And so that means that 6 divides 7 to the k plus 1 minus 1. And that means that p of k plus 1 is true. And so what did we assume to show that p of k plus 1 is true? We assumed that p of k is true. And so the inductive step is that p of k implies that p of k plus 1 is true. And that's what we showed. And so now we can say by mathematical induction, p of n is true for all integers n is greater than or equal to 0. This is more like a ritualistic conclusion to all mathematical induction proofs, in the same way that the beginning of my inductive step is a little bit ritualistic as well. I always say let k be an arbitrary integer with k greater than or equal to whatever the lower bound is on the base case, and assume that p of k is true. So there are some ritualistic parts to this proof. Anyways, thanks everyone, and I'll see you in the next video.